Imagine you were asked to explain the meaning of a vector. What would you say? Picture yourself back in the classroom, perhaps nodding along as the teacher explains its three components in a neat column. You might recall sketching arrows in a three-dimensional coordinate system. For this particular example, you have to walk 1 unit in x direction, 2 units in negative y direction, and 3 units up to find the position of the tip of the arrow. It turns out that these two definitions only scratch the surface of what vectors really are. Vectors are not just abstract concepts confined to textbooks or math explainers. They model the essence of locations or motions. They represent forces or even linguistic properties inside a large language model. But what about the coordinate system? It is merely a gateway to understand the meaning of the vector, a tool that transforms its direction and length into tangible numbers. Moreover, there is a lot of freedom in the choice of such coordinate systems. Imagine a second person that wants to describe the same vector in a rotated coordinate system. For simplicity, we first rotate the coordinate system around the z-axis by an angle of 90 degrees and read off the components of our old friend in the new coordinate system. However, we are not limited to rotations by 90 degrees. In principle, the new coordinate system can be rotated by any angle. The corresponding components transform smoothly with the rotation. You can see how we rotate back to the original orientation, overshoot slightly, and finally get back to where we started from. It is possible to relate the coordinates of the rotated coordinate system, which are labeled with a tilde, to the coordinates of the original system. This rotation is just a linear transformation which is expressed by a rotation matrix. If you position yourself inside the new coordinate system, it looks as if the vector was rotating away in the opposite direction. Therefore, the components of the vector in the new coordinate system are related to the old ones by the inverse rotation. There are two ways how the rotation matrix can be inverted. You can either replace the angle by its negative value or transpose the matrix, which means that you exchange rows and columns. In either case, you just switch the signs in front of the sign function. You just witnessed that a vector is much more than just a matrix with a single column. It is an object that obeys precise rules of transformations when we change our coordinate system. One of my teachers at university told me this fact repeatedly when he was asked about the meaning of tensors, which are generalizations of vectors. But I never really understood the important implications of these words until I found objects that look like vectors, but if you look very carefully, you will find out that they are actually not compatible with changes of the coordinate system. The aim of this video is the presentation of such an object. We will show that the cross product in 7 dimensions returns a vector-like object which does not satisfy the transformation properties that we just highlighted in this introduction. Before we can really appreciate this 7-dimensional cross product, we have to learn a bit more about rotations and the cross product in 3 dimensions. Then we can lift the cross product and the rotations into 7 dimensions. Although the cross product in 7 dimensions shows the same basic properties as the cross product in 3 dimensions, we will see that the result of the product, unlike in 3 dimensions, cannot be called vector, strictly speaking. Although one could be disappointed by the fact that the cross product in 7 dimensions is not compatible with rotations in general, we can convert this disappointment into an exciting discovery. In the humble attempt to find a few special rotations that can coexist with our 7-dimensional cross product, we will construct a subgroup of all 7-dimensional rotations, which turns out to be nothing less than the famous exceptional Lie group G2. So far we only looked at rotations around the xy plane, and we are familiar with the corresponding family of rotation matrices that are parametrized by the angle phi. It takes a full turn of 360 degrees or 2 pi to get back to the coordinate system that we started with. Similar rotations can be performed for the yz plane. Here we introduce a new angular variable theta to indicate that this rotation is completely independent from the rotation around the xy plane. And of course, there is a third possible rotation of the xz plane, which we denote by the angle psi. When you compare the rotation matrices, you will find that only the position of the sine and cosine terms change. The one in the diagonal always indicates the coordinate direction that is unchanged by the rotation. In 3 dimensions, we usually refer to it as the axis of rotation. The concept of a rotating plane can be generalized to higher dimensions. The concept of an axis of rotation is doomed to fail in higher dimensions, because there will be more than one coordinate direction that is left unchanged by a particular rotation. The combination of any 2 rotations forms another rotation. These are special orthogonal matrices. They have a determinant of 1, and the transpose of every matrix is equal to its inverse. These matrices represent a Lie group abbreviated with SO3. Each and every possible rotation that you can think of in 3 dimensions can be written as a product of these 3 families for particular choices of the so-called Euler angles phi, theta, and psi. The principal nature of such rotations does not change when we transit to a 7-dimensional space. Only the number of families will increase from 3 to 21, because there are 21 different coordinate planes in 7 dimensions. But let's not get ahead of ourselves. Before we leave the comfort zone of the 3-dimensional space, we should remind ourselves of a few properties of the cross product. Given 2 vectors a and b, there is a unique way to construct a perpendicular vector in 3 dimensions. In the animation you can see how the components of the cross product are computed from the components of the 2 vectors a and b. With this choice of sign, the 3 vectors form a right-handed system, and the length of the third vector is equal to the area of the parallelogram spanned by a and b. This cross product is commonly also called vector product, because it maps 2 vectors into a new vector. We have to be careful at this point. The product a cross b should only be called vector when it transforms like a vector under rotations of the coordinate system. We can check for our families of rotations that they are compatible with this cross product. Here, compatibility means that we can compute the product a cross b and then rotate this product into our new coordinate system. Or we can first rotate the vectors a and b and then compute the product. The result should be the same. We first rotate our 2 vectors a and b, and we rotate the product a cross b. Next, we convince ourselves that the cross product of the rotated vectors is the same as the rotation of the product of the original vectors a and b. This is a tedious calculation, but it will work for any 2 vectors and any rotation. You should try it yourself, since it is not at all obvious and relies on properties of the sine and cosine functions as well as on the particular definition of the cross product. You might be tempted at this point to say, hey wait, we have a product vector that is orthogonal to both the vectors a and b. Additionally, its length is fixed by the area of the parallelogram. What on earth can go wrong when we rotate our coordinate system? The product vector has no choice but to rotate in the same way as expected to maintain orthogonality and length. And you are absolutely right. But exactly this intuitive justification breaks when we add 4 additional dimensions. They will enlarge the orthogonal space and partially mess up the transformation properties of the cross product. How does the cross product in 7 dimensions look like? Well, let's start with a warning. There's more than one possible definition for a cross product in 7 dimensions. Nevertheless, the following discussion is universally true for all choices of a 7-dimensional cross product. For convenience, we relabel our coordinate directions x, y, and z with indices. The 3-dimensional cross product is rewritten correspondingly. Instead of x, y, and z, the components of a vector are denoted with indices as well. This makes it easier to introduce 4 additional dimensions without having to use letters that never have been used for coordinate axes before. Now we can introduce 7-dimensional vectors, which we label with capital letters. If all higher dimensional components of our vectors A and B were 0, we'd recover the standard 3D cross product. However, if the extra dimensional components are turned on, there will be contributions to all components. It is tedious but straightforward to verify that this cross product satisfies the same basic properties. The product is orthogonal to its factors A and B, and the third relation encodes that the length of the cross product is equal to the area of the parallelogram spanned by A and B. This looks all very nice so far, right? Before we rotate our 7-dimensional coordinate system, let's make sure that we understand how special orthogonal matrices and their represented rotations look like in 7 dimensions. Similar to the extension of vectors from 3 to 7 dimensions, we can extend our 3-dimensional rotation matrices by simply adding 4 further rows and columns. We have to make sure that there are 1s along the diagonal and 0s everywhere else. Then we still have a rotation that only turns the x1, x2 plane, but this time inside a 7-dimensional space. Just as in 3 dimensions, we swap the position of the sine and cosine components to generate all possible simple rotations that only turn planes spanned by 2 coordinate directions. In 3 dimensions, the position of the minus sign was chosen in such a way that the rotation was always counterclockwise with respect to the axis of rotation. Here in 7 dimensions, we don't worry about this orientation and always keep the minus sign above the diagonal. Now we are ready to investigate how the 7-dimensional cross product transforms when we rotate our coordinate system. With computer algebra, one could work it out for the general case, but here it will be more instructive to look at one particularly simple example. We choose the unit vectors of the x1 and x2 direction as factors to start with. Since all extra-dimensional components are 0, we end up with the unit vector in x3 direction as the expected cross product. And of course, it is easy to check that this transforms nicely when we perform a rotation in the x1, x2 plane. Obviously, the product is not affected by the rotation at all, since there are only 0s in the first 2 components. When we compute the product of the rotated factors tilde a and tilde b, the trig identity of sine and cosine squared establishes the agreement with the rotated product A cross B. Now let's courageously turn on an extra dimensional component in one of the factors. This causes one additional contribution to the cross product. Let's check again the compatibility with our rotation. Obviously, the product is still not at all affected by the rotation. However, when we first rotate our factors, one more term is turned on inside the computation of the cross product, and the product of the transformed vectors no longer matches the rotated product A cross B. It's kind of inconceivable, but it somehow means that not only the components of the cross product change with the rotations of the coordinate system, but also the orientation of the product itself changes relatively to the orientation of its factors. However, it is too early to start crying. If you look at the mismatch between the two quote-unquote vectors, you might feel tempted to add an additional rotation that turns the 1 in the 5th component of the right-hand side into a corresponding sine and cosine pair. The required rotation has to turn the x5, x6 plane, so it seems when we combine a rotation in the x1, x2 plane with an equal amount of rotation in the x5, x6 plane, we might be able to restore the necessary transformation properties of the cross product. And indeed, for such a combined rotation, any choice of vectors A and B and their product transforms as expected. The product of the rotated vectors tilde A and tilde B is the same as the rotated product A cross B. In a similar fashion, you can find 13 further combinations of rotations that are compatible with the cross product. And hold your breath, these 14 families of double rotations form a subgroup of the larger 7-dimensional rotation group SO7. And guess what? These 14 families furnish a representation for the exceptional Lie group G2. We presented this group more or less as an accidental discovery, but of course there is a deeper reason for this coincidence. Probably some of you want me to say something about the underlying secret. The mere existence of the cross product in 7 dimensions is based on the multiplicative properties of the unit octonions. And G2 turns out to be the automorphism group of these octonions. As always, this opens the door to a whole new fascinating area, and we save this for another time. However, there's one last thing to do. If you are like me, you will most certainly find it unsatisfying to just being told that these 14 families of double rotations represent the exceptional Lie group G2. If this sentence sparks additional curiosity, then you are invited to stay for a few more minutes and see how the root letters of the G2 algebra is explicitly computed from these 14 families. For me, G2 has been like a mystery for many years. It seemed that there was no simple definition for it. Unlike rotations or unitary transformations, it did not belong to a larger family of Lie groups. Moreover, it appeared as a holonomy group of manifolds for compactifications of 11-dimensional supergravity. I was a bit disappointed when I finally understood that it is just a subgroup of SO7. It is just a bunch of rotations after all. If you are faced with an unknown Lie group, its Lie algebra is a good starting point for investigations. The algebras of semi-simple compact Lie groups are completely classified. The one for G2 is schematically represented by this stinking diagram. It encodes that the algebra is two-dimensional, that the two simple roots are separated by 150 degrees, and that one root is longer than the other one by a factor of root 3. Two such simple roots labeled with alpha and beta are displayed in the diagram. The remaining elements of the root lattice are linear combinations of these simple roots. There is a good portion of linear algebra computations that transforms the 14 families of rotations into 12 vectors of the root lattice. It would be a nightmare with pen and paper, but it's quickly done with a computer. Just lean back and enjoy. The most tedious part is filling the notebook with the 14 rotations from scratch. We create a function for a rotation in one generic plane of the 7-dimensional space, described by two coordinate directions m and n, and one angular coordinate phi. The 14 families are entered as the cross product preserving double rotations. These families are then converted into generators of the Lie algebra by just taking the derivative with respect to the angle of rotation. All matrices are antisymmetric. The properties of such matrices are contained in their eigenvalues, and it is usually possible to find an orientation of the coordinate system such that some of the generators become diagonal. However, not all generators can be diagonalized in the same coordinate basis. The largest set of simultaneously diagonalizable generators is called the Cartan subalgebra. To find it for our case, we pick the first matrix and find another one that commutes with the first one. For our choice, it is the generator of the 13th family. The two generators span our Cartan subalgebra. In order to obtain a nicely rotated and scaled root lattice, these two generators have to be orthogonal with respect to the standard inner product for matrices. So we rotate and scale them appropriately. Once our Cartan generators are calibrated, we have to search for linear combinations of the remaining generators that are eigenvectors of the Cartan generators with respect to the commutator operation, which is the multiplicative operation of the Lie algebra. The eigenvalues constitute the root lattice. We find appropriate linear combinations by brute force. All generators are just linearly combined with unknown coefficients, and then the eigenvalue equations are just solved for arbitrary eigenvalues kappa and lambda. All sensible solutions are collected and the root vectors are displayed visually. Of course, this was just a sketchy run-through. This root lattice gives evidence to the claim that these 14 families form the exceptional Lie group G2. We discussed such root lattices and Dynkin diagrams related to reflection groups in earlier videos. One of them is linked to the screen right now. The second link leads to an interesting mathematically bulletproof discussion of cross products in various dimensions by Micheal Penn. I hope that we managed to build an illuminating bridge from the elementary cross product that everyone learns in school to advanced topics in algebra. We've seen that a vector is so much more than just a collection of numbers. namely it is equipped with very particular transformation properties. We've also seen how rotations act on vectors in 3 and 7 dimensions. We got some ideas about Lie groups, their Lie algebras, and their classification with root lattices. There's much more to present and more to learn, but this has to wait until later. We say goodbye while transforming the SO7 root lattice and the G2 root lattice into one another.